do about it, and what situations that you have to be careful to make sure this is not, or situations where this could rise, and you need to make sure and protect yourself against it. All right, so this is something that we never really told you about flip-flops when you took Intro to Digital Design, and that is that, when we talk about a clock edge, it does happen very quickly. I mean, really nothing, no voltages ever really change instantaneously if there's any capacitance at all. And of course, there is always some capacitance. So just like we can say in physics that you can never change the velocity of something instantaneously, because if it's got mass, it would take an infinite amount of energy. It's the same thing with changing voltages. If there's any capacitance at all, it's always going to take a little bit of time to change. When we model this, though, it's just this straight up and down line, this discontinuity. It's really more like this. If we zoomed way, way, way in on it with an oscilloscope, maybe there'd be a little rounding, like a charging up thing of a capacitor. Around this edge, there's some timing that has to hold. And the time between the clock edge, wherever that's defined, and usually on here it's like the midpoint, the time or how much time the circuit needs to observe the input signal reliably is called the setup time. So you have to have your data there before the clock edge by a certain amount of time. Now this makes sense because if we think about what the input stage of a D flip-flop would look like, it's got to measure the voltage somehow. And again, voltages don't change instantaneously, so it takes a little bit of time. Now this may be very small. This may be 20 picoseconds or something, but it's not zero. There's also a period of time after the clock edge that the voltage has to be stable for the flip-flop to work properly. And that's called the hold time. You can't change the data in between, during either one of these. Sometimes, depending on how the chip is designed, the hold time may be very small, or the setup time might be very small, and they've kind of shoved all of the timing into one or the other. But the setup and hold time together make this window in which the data has to be stable. Okay, well, you might wonder then, what happens if you don't? Like, well, you can change the data whenever you want to. What if you choose to change it right on the clock edge? Well, let me show you what happens. Suppose we have a NOT gate, which is kind of just the simplest one to talk about. And we have some input and we have some output, A and Y. If I were to plot those, so as A gets higher, this is the voltage A, and this is the voltage on Y, what we usually see is that there's this function like this. Now, if it's a really great inverter, this time, this voltage range here is going to be very small. But the fact is, there is a slope here. It's a continuous function. And what I would like to convince you of, or maybe just kind of tell you is the truth, and then you can convince yourself, is that there is some point on here, there is some point on this curve to where Y equals A. And where that's the case, what I could do is this, and I could actually stick it at this point. Let's say that this is Vm for metastable. If I make this V sub m the output somehow, or I make the input that, then what will happen is that gate will get stuck there because it's got an input of V sub m, which generates an output of V sub m, which generates an input of V sub m. So it's not a logic high, it's not a logic low, it's right in the middle where I'm not supposed to be hanging out at all for my digital logic gate. I'm supposed to be at high or low, but I'm stuck in the middle of this metastable voltage. these kind of logic gates are unstable. Like they don't want to hang out there, but it's a little bit like if I have this is the example they use in the Altera documentation, which by the way, there's a white paper out on Canvas under this week's module that's all about metastability and clock domain crossing. I would like you to read it. And the example they used is that if you take a hill and you put a ball on top of it, most of the time the ball's gonna roll down here, or the ball's gonna roll down here, right? But you might get it right on the top and it just sticks there for a while. And it might take it some time to roll off. Now, if the ball starts out down here, obviously it's gonna roll off real quick. Or if it starts here, it's gonna roll off real quick. But there is some point that if the ball happens to land right on the top, it might sit there for a little bit before it finally rolls off. That's what this V sub m point is. Yes, the thing's unstable, meaning it's gonna go one way or the other, but if your voltage, if your input voltage is about right there when the thing clocks, it's gonna get stuck on top of that hill and it's gonna stay there for a little while. When that happens, that's called metastability, and that's what causes your gate to do something like this. The output of your logic gate, you might have a high, you might have a low for a while, and then you get this weird squiggle in the middle for a while, and then you go high. This is a metastable event. That is a metastable event. We got these nice highs and lows, and then we got this funky thing in the middle. And I don't know if you remember from building these circuits back in 2214, but inputs of logic gates don't like things that hang out in the middle. All right, so that's the key. That's what we're trying to. That's what we're trying to avoid, is this metastable error in the output of the gate. So suppose I have like a 1 kilohertz clock. It's 1 kilohertz, so this is something like a millisecond. So that's something like a millisecond. And let's suppose that my setup and hold time are maybe altogether 0.1 nanoseconds. That's my setup and hold time right around there. I think that may even be a little longer setup and hold time, but let's pretend. Zoom in a little bit more there. Now, if I'm gonna flip a switch, and I've got, let's say one of the buttons on our DE10 light board, so our key 1 or our key 0, I'm gonna press the switch. The question then is, well, what are the odds? What are the odds that I'm gonna push that button during this setup and hold time? Pretty small, right? And if it's a uniform probability, so like probably, like it's an independent event, the clock and me pushing the button are two independent events, we can assume, well, this is somewhat uniform distribution. And I could say the probability that it's gonna have this, that it's gonna violate the setup and hold time is 0.1 nanoseconds over 1 millisecond, which is something like 10 to the minus 13. I'm doing that in my head, so I might have it a little bit wrong. Really, really unlikely that that's gonna happen. Now let's suppose that I'm working on my DE10 light board, and the cycle is 20 nanoseconds. And the setup and hold time is still 0.1 nanoseconds. What are the odds that I'm going to violate the setup and hold time when I push my button? Well, pretty good, a lot better. The probability of error there is 0.1 over 20, which is, I don't know, 1 over 200, which is 0.5%. So there's a 0.5% chance every time I hit that button that I'm gonna violate the setup and hold time. And push it 200 times, it's gonna happen, I'm gonna get this metastable event. Well, that's a lot of button pushes, sure. But if I'm putting data in, so suppose I'm streaming some data in from whatever, from a sensor or some kind of thing, and I'm not clocking it from my FPGA. In other words, whatever I'm reading the data in from is not synchronized to the 20 megahertz clock. Then the data coming in looks somewhat like a random event. And so I should expect that every 200 bits, in this case, I'm gonna trigger this metastable event. And it's gonna lead to probably a bit error. Now the probability that there's a bit error is, so if I take my clock cycle, and I've got some piece of data that's coming out of a logic gate. There you go. This is the mice. I need that, we need to turn I don't know if I can get this installed sideways where it's longer to the other way. That's probably not going to do that. If I have this metastable event, will the metastable event happen longer than the clock period? Or in other words, is this funkiness still going to be going on by the time I clock this bit in on the next cycle? If it is, I've got a problem. If it's able to resolve itself before the next clock edge hits, I might be okay. Well, and then you have to account for the fact too that it's not, like there might be this might be affecting other logic down the road. It needs to be resolved quite a bit before the next clock edge. If I have a metastable event up here on my 1 kilohertz clock, yeah, almost guaranteed that metastability is going to be resolved by 1 millisecond, which is like eons in FPGA time. But if I've got a very fast clock down here, then it's not going. There's a good chance it won't be resolved by the time I hit that next rising clock edge. As the clock gets faster and faster and faster, and as the margin that we have, the leftover time we have between when our results get calculated for any particular block that we've written and the next clock edge, the less timing slack there is, the more likely this metastable event is going to cause us to miss the next rising edge. Well, they do a good job in the paper of really nailing all that down and giving you some formulas and letting you calculate statistically what the mean time between failure is. In other words, how long should you expect to be able to run this thing without having a bit error? And I present it like bit errors are the end of the world. They're really not if you're expecting them and you've got some algorithm to correct them. I mean, if you take something like your, if it's like a wireless communication thing, like your wireless router, it can live with bit error rates as high as 1 out of 100 bits being corrupted if you put enough error correction algorithms in your device. You can recover from it. But typically, your FPGA is not expecting to have very many errors in its data stream at all. So these kinds of errors are a little more serious. All right, so where we should expect this then, where we have to guard ourselves against this metastability, which is again caused by the fact that we've changed the data during the setup and hold time. You can't see where I'm pointing. It's a good thing they put a monitor in the back of the room, or that we would never notice. Again, it's caused by changing the data in this setup and hold time. There's 2 cases where this can happen. Case number 1. Data is not synchronized at all. So in other words, it's coming from some kind of sensor, it's coming from some kind of device that does not have a clock running to it at all. So push buttons, a switch, analog detectors, any kind of thing that you hook up to the system that's not clocked and you're using that input, you're using the output of that device as an input, that has got the possibility of violating the setup and hold time. If it doesn't even know when the clock edge is, how can it avoid it? Number 2, data is synchronized, and I should be saying input. I forgot, okay, synchronized to another clock. So the data is synchronized, but not to our clock. So for example, we're bringing in some UART data, which is like in microprocessors, you would have called it the serial interface. And it's slow, you know, it's not 9600 baud or whatever you use, 19.2K, whatever you use. But the clock that's used for that is not the same clock that the FPGA has. It's not being clocked from the 20 megahertz, or 50 megahertz clock we have on our FPGA. So it is synchronized to something, but not to our system. And there will come a time eventually where we'll violate the setup and hold time. If you want to make sure that your two systems don't have this problem talking to each other, and you're bringing data from one system to another, and you want to make sure you never have this kind of violation, what you have to do is you have to run both systems off the same clock. This is a huge problem with like telecom systems. You can't afford to have any difference in the clocks at all. So what you have is you have one side of the connection is the timing source, and the other system uses a phase lock loop to exactly match the frequency of the clock on the other end. And that way you guarantee that the clocks, you're never going to slip a bit. You're never going to have one more clock cycle on either side of that link, because if you do, you're going to have a bit error. So that's what you have to do. Now sometimes it's not possible to do that. It's not possible for everything to run off of a single clock. So what you do instead is you use a data synchronizer, like for our case. So let me show you what a data synchronizer is. So we have data input coming from another clock domain. Now what the phrase clock domain means is it may be clocked, it may not be clocked, but it's not clocked by our clock. So everything, for example, on our FPGA board that is clocked by the 20 or the 50 megahertz clock 50, is within one clock domain. But I might bring signals in that are clocked from something else, they're from a different clock domain. So when we have those two things meet, what we need is a clock domain crossing, and we do this with the synchronizer. So we have this data, and we bring it in, and we put it through the flip-flop. This is our local clock, the clock on our board. Now what we hope is, you know, of course there's going to be a possibility that we're going to fail the setup and hold time here, that we're going to violate the setup and hold time. So what we're going to do is put another one right here. This nomenclature means that the clock is the same for both of the flip-flops. Okay, so suppose that the data comes in and the data changes during the setup and hold time. So the setup and hold time violation, which causes a metastable event on the first flip-flop. If this metastable event resolves itself within one clock period, then we're good. We're golden. We're assuming here that the ball is going to roll down the correct side of the hill. It just may take it a little longer than we want. But as long as it rolls down in one clock period, we're good. Because then it's going to eventually, before the rising edge, get to the right value. This flip-flop's going to capture it correctly. The data out of here is going to be good. It won't, that metastable event won't have propagated into the rest of our logic. But there is a small probability, and you're wondering, well, what is the probability? It's, look in the white paper, they've got it. There is a small probability, especially as the clock gets very fast, that this metastable event will not resolve itself within the amount of time before the next clock edge, and that metastable event will propagate out of this flip-flop, causing a problem. So we put another one. We can put another one if we want to. So if this metastable event doesn't resolve itself, and it propagates through here, we're gonna drop the ball again. Maybe we'll get a better landing, and it will roll off the hill. Now, given that this is a relatively small probability that it won't resolve itself by the time the next rising clock edge rolls around, now we've got that probability squared. So it's even a much smaller probability. But if we wanted to, we could throw another one out there and drop the ball again. And it's just a matter of how many flip-flops can you afford to throw at it, and how bad is it if you get an error. Most of the time people stop with 2 or 3, and that's good enough. But this is what you would do anytime you're crossing a clock domain, meaning the data is coming from a place that's not being clocked by our local clock. You've got to run it through a synchronizer like this. If you don't, and you're pumping any decent amount of bits through there at all, you're going to get bit errors that are going to mess your design up. It's going to cause weird, glitchy errors. All right. So that's the business about synchronizers. So you should start doing that on anything that you write in the future. I think we've probably got one more project with them. We need to get it out there pretty quick if we do. But that's what you would need to do this on any of your inputs, like your buttons, your switches. And of course, you can write one module to do this for you. We looked at that last time when we were talking about how to do the blocking versus non-blocking operators. This was actually one of the examples. I wanted to take this example and also modify it to do something else. And that is, we have, a lot of times in the projects that are previous projects, there are times you wanted to push the button and you only wanted it to do one event, so like, you might have this button push, and this might last for like 10,437 clock cycles. Unless you're like super fast, that can actually happen. But what you really wanted when you push the button is you just wanted one button press. Well, there's a way to do that. You don't have to make a big complicated state machine. You basically do this. Let's do when you let go of the button, so it goes from 0 to 1. So we'll do this. So you take and you sample key, which is the button of the button we're pressing. You get 2 samples of that, basically 2 successive clock edges. And you're looking for the case where the earliest one was a 0 and the later one is a 1. See, I inverted the bottom one. And when that signal goes high, that means that you got, that you're detecting this edge when the button comes back up. You could do the falling edge if you wanted to, just reverse which one is negated. So this is a way that you can detect edges using a couple flip-flops and an AND gate, maybe a NOT gate. But notice that we've already got this part of it, we've already got that like right here. So what you can do is make a module that not only synchronizes the data, but also detects edges. And basically all you have to do to make that happen is take this data line and just put your AND gate here, invert this one, put your AND gate here, and there's your edge. And there you go. So you can put this, and if you wanted the raw data, just run it down here, no big deal. So this is a nice little module to write and have that you can just, anytime you wanna bring a key or a switch or anything in, you just instantiate this module. Hook your clock up to the clock, hook your data up to the key or switch you're talking about, and then just connect this to the logic that's used in your, where you know, the enable for your counter, for example. That was one where we're always, you don't want, you only want one enable pulse every time you push down the key. Well, that's gonna do that for you. Okay, so questions about, that's a lot bigger there than it is on my little TV. I'm like, no one can read that. So I'm looking up at that little TV and I look over here and it's enormous. Okay, so maybe I need to get a little better with the technology. All right, so what questions do you have about metastability or clocks or synchronization? I wanted to make sure and spend an entire lecture on this because if the one thing that, like, if you go and you interview somewhere and you tell them that you did FPGA work and you know Verilog, the question you're most likely to get is, how do you handle a clock domain crossing? Because it's a huge source of errors, and kind of people who self-teach themselves don't think about it. And so I want you to go, I use a synchronizer. That's how I do. I run it through a couple flip-flops. Hopefully they'll nod and they'll please, that's the plan. But it's a huge, it's something that's important that you know, so make sure that you keep it somewhere in your mind when you do an interview and they ask you that question. Or you're working on a project at wherever company or organization you land in. Make sure you keep it in mind. Okay. Well, that's the new stuff for today. If you've got questions, hang around and ask them.